Hello, it's Keith here. Today we're going to do another special episode. We had a look at the Spectrum Next a little while ago. This time we're going to look at another of these prototype machines that's being developed, known as the Commander X16. Now, I have to point out this is at a much earlier stage than the Spectrum Next, so it's very possible that the example I'm giving today won't end up working because they might change all kinds of things. But I thought it'd be curious to have a play with it, and I wanted, being as I was now starting to break out into these newer machines, to do them both at the same time, just to sort of be on a parallel level with both of them. Now, unlike the Next, the Commander X16 is 6502 based. It's using a 65C02 because it's based on the Commodore 64. So just like the Spectrum Next was a more powerful ZX Spectrum 48K sort of, the Commander X16 is a Commodore 64 essentially. And just like the Spectrum Next, we can actually compile some basic Commodore 64 code and pretty much run it. And that's what we're going to be doing today. So I've taken one of my old Hello World examples and I've upgraded it, and it's going to work in 256 colors on the Commander X16 emulator. And before I keep talking and making claims I can't back up, let's actually fire up the emulator and see it running. So here we've got a Hello World example here. We've got the 256 colors filling the screen here. The screen in this mode is at 320 by 240 here. It can have a high resolution mode as well, but this is the one I'm using here. And we've got Hello World, and this is my bitmap font that I use in all my other tutorials. It's a 1-bit per pixel font, and I'm converting it to 8 bits per pixel for the screen. So there we go. So that's what we're going to be learning how to do today. Now, the emulator I'm using is X16EMU, which is open source and free, so I suggest you go ahead and download that. There's some documentation and some sample code from the official developers of this, so again, feel free to look at that. That's what I've used to write these tutorials today. But we're going to go over my code and see how it works, and maybe it'll be interesting to you. Of course, you can download my source code. Go ahead and do that. Now, the fundamentals that we're using today are the new ports. The new graphics chip seems to be known as the Vera hardware, and so we have this set of ports here, and essentially what it does is it's got an extra bank of memory, and some of that memory is video RAM, conventional video memory, which is just the bytes in that memory make up the screen, and some of it's hardware ports that we can configure. And essentially it's a 20-bit address bus, and we use these 3 ports here to select an address, and then we use one of these data ports to read or write the address that we selected, and we're going to see a lot of that. So I'm just briefly going over it now because we'll see it more practically later on. Now, the video memory is made up essentially something like this. So we've got our basic video RAM in this address range here, and that's what we're going to use to make up our screen, and that's what we were writing to draw those lines we just saw and the Hello World text. We've then got some controls. There are apparently 2 layers. I'm only using layer 1. I've not played around with layer 2, but I guess it's capable of parallax. 256 color parallax would be very nice. It's also capable of hardware sprites, so lots to enjoy there. But we're going to be using just one of these layers. And again, I'm just showing you this in passing. We're going to go over it in more detail when we actually start looking at the code. So, please go to my website, link will be in the description below, and download this Hello World example if you want to play around with it. You can compile it with just a conventional assembler. I'm using Vasm, and I run it via a batch file with the X16EMU that we're running it today. Now, one thing I've added is I've added an extra switch. This is my Vasm script that I use. So we're just using old style Vasm here. We specify the source assembly file here. We are specifying to output a CBM program. We're just creating a conventional Commodore 64 PRG file, and the X16 Commander will run that just fine. Disabling case sensitivity, checking labels here. I use some symbols in some of my code. We don't need to worry about those though. You can just ignore these. But as I say, the main thing is I'm enabling the extra 65C02 commands that the system's got because I wanted to try and make my code as good as I could for today. So that's what we're doing. And then once we've created a PRG file, we can just run it with X16EMU just by specifying /run on the command line and the name of the file we've compiled. So that's how I do things. I get batch files set up, I automatically run them from my function keys on my keyboard, and that's how I can test things quickly because I make lots of mistakes. And if you make lots of mistakes, then if you can compile quickly, then you can fix them more quickly. Okay, so what I'm going to do now is I'm going to go through the source code and I'm going to describe how each part of it works. And so through the way you should get a basic idea of how to use the basic 256 color bitmap screen. And from that, maybe you can play around and do something of your own. We're probably going to go over the other details of the hardware sprites and the tile maps and things later on. It will kind of depend on how much interest there is in this system. So please let me know if you're interested, drop a like or make a comment, whatever. So we'll go over the basics and what we do from here on, we'll see. So the first thing is I'm defining some 0-page entries here. We need some temporary variables and I've defined them here. So I tend to use 0-page labels that mimic the Z80 registers because I was a Z80 programmer before 65021, so that works nicely for me. So we're using a HL pair here, a DE pair here, and these are 16-bit pairs which we'll use for calculation, and a backup of the accumulator here. Now beyond that we've got some definitions for the registers of the Vera hardware. So when we define a memory address, we need a high, a mid and a low byte that make up the 20-bit address. Now the top 4 bits of the top address are actually the increment counter. We will want our data address to increment each time we write to it, so that's always going to be basically be 1 in our examples, but we need to do that. And then once we've written to that, that should be a 1, not data port 3. There's no data port 3. So the address here is data port 1, and we're going to label that V_D1. And then there's a control port, which we only need to write to once, actually, just to initialize and configure the data port, so that when we set the address, we're configuring data port 1. So these are the only registers we're going to need today of the graphics hardware, because essentially everything we're doing is just writing specific memory addresses using these 3 pointers to the memory addresses that make up the Vera hardware. Now, next we have an initialization routine for our program file. So this is just a basic Commodore 64 starting routine. We just need a set of bytes here to start our program up. And then that will effectively start our program at this byte just here. And so then on, we just put our assembly commands, and that's all we need to do. So first thing we want to do, we want to set up the hardware so we can write bytes to memory. As I said, we use the Vera control. We need to set the bottom bit to select a port, and by setting the bottom bit to 0, it says when we select a memory address, we are defining Vera data 1 here. Because if you remember, there's a second Vera data port, but there's actually only one memory address set of registers. So I guess we can use this to use data port 2 for a different address of data port 1, maybe if we're copying banks of memory or something, I guess. But anyway, as I say, that's what we're doing, but here we just need to set it up at the start to get that memory address correct. And then we're going to select a memory address here. So here we're using a command called setVera_HML. Now I'm going to be using this a lot, so let's take a look at this. Now, if you remember, we defined some pointers VH, VN and VL, and we're pointing them to these 3 addresses here as a quick way of setting the high, medium and low addresses of the Vera hardware. Now what I'm doing is I've defined this function here where we're using the accumulator as a top byte and writing that to VH, the Y as the mid byte and writing that to VM, and the X as the bottom byte and writing that to VL. And we're going to use this command over and over again every time we want to set in a memory address. And I've made sure that the addresses are in consecutive order, so the first byte's the top one, the next byte's the middle one, and the third byte is the bottom one. Now you can see here we're writing 140040. If you remember, the top nibble is actually the increment counter. You can see I've kind of marked that here. So effectively we're setting 40040, and I've written that here. And this is the DC video address. Where's that? Well, that is just here. And what this does is it allows us to turn on the VGA with the bottom bits here. And that's what we're doing here. So effectively all we're doing here is we're writing a 1 here to turn on the VGA, and the rest of the bits are just 0, and we store that to D1, which is the data port, effectively setting that memory address that we selected here, 4040. Now, as soon as we do a write here, because we've got that increment set just here, then the next write will appear to 40041, and that's the horizontal scale. Now, a scale of 128, I believe, is normal. A scale of 64 doubles the size, and we're setting 40041 and 40042, the X and Y scale, and we're doubling it. This is because by default the screen is 640 by 480, and I think that actually causes some memory problems because there's not that much memory for bitmaps. So I'm setting it to 320 by 240 because, to be honest, with these 8-bit systems, that's my target scale anyway. So we're setting that kind of scale here. So now we've got a screen that's sort of getting to set up. Let's set up a palette, and that's what we're doing here. The palettes are at 40200 here. Let's have a look at that list again. Here we go, here's the palettes. So there's 256 colours, each one takes 2 bytes, and they are made up of 3 nibbles. There's a red nibble, a green nibble, and a blue nibble. Now the red comes after the green and blue, but that's because it's a little endian systems, so it's kind of writing backwards, if you see what I mean. So what we're doing here is we're setting up the port by selecting this, remember, with that top bit as 1 for increment. And then what we're doing is we are setting X and Y, and we're setting them in such a way that we're going to write 256 pairs of bytes to the memory. And we're loading in the address palette into my 0-page H and L pair, which you can see here. And we're using a Y as an offset here. And we're just looping around, basically reading in bytes from ZHL and writing them to the data port of the hardware here. Now, if we have a look at my palette right down the bottom here, here it is. So we've got the background as dark blue, the first colour is yellow, the next colour is cyan, and the next colour is red. And you can see that here because the top nibble's unused. Then you've got red, green and blue, which is kind of backwards if you remember. You had green, blue and red here, but that's because, as I said, it's a little endian system, so, and we're defining these as words, so it looks more logical here. Now after that, I'm using just, you know, incrementing each of the colours one at a time, just for some testing here. And if you remember, that's what we can see here, blue background, yellow text, and then you can see here we've got red, green, blue, grey. So we're just going through all of the colours here as a test, and I just wanted to give a nice range of palette colours to see everything was working okay. So we're loading in our palette here. So once we get to this point here, we've set up our palette. So we've got a screen on, we've got a palette set up. Now what we're going to do is we're going to set up layer 1, the bitmap layer that we're going to be using in this test. Now again, we need to use one of these sort of video memory registers here. So this time we're using this one here, layer 1 control 0 here. And we need to turn the layer on with the bottom bit, and we need to set the mode with these top bits. And the mode we're using here, we need to set all the bits to 1, which sets the 8-bit per pixel mode, the 256 color mode. Now to be honest, I tried to use the 4-bit per pixel mode and I couldn't get any sense out of it. I think maybe it's this. Now, I was getting weird patterns like this with the 4-bit per pixel mode. It seemed like it seemed like maybe there was a mask enabled or something. I couldn't find anything, and I don't believe the documentation currently documents the other modes. So maybe I'm using it wrong, maybe I'm being really thick, or maybe the emulator doesn't implement it yet. So anyway, the 8-bit per pixel mode seems to work great, so that's what we're using here today. Now, we're storing this byte configuration here to 400 here. But then we need to set some of these other ones, layer 1 control, which is relating to tile maps. These aren't really very relevant. I think it's the tile base. I think the tile base actually defines the memory base for the bitmap modes. I think the map base doesn't do anything. It's a tile base that defines the memory base. But we want that to be 0 anyway, because we're using the start of the memory range for our bitmap area. And then setting the scrolling here. So we're using this special 65C02 command STZ, which just stores a 0 to all of these addresses, just sets them up with a 0, and that'll do quite nicely. So now at this point, if you were taking my code but stripping everything else out, at this point you've got a screen set up, you've got the layer set up, and you've got the colors so that the things you start to write will actually be visible. So you would want to delete everything after this if you're just starting from scratch with a working screen. But we're going to have a look at the test code that I've got set up here. So the first thing I'm doing is I'm starting the video ramp at 0, 0, 0, 0, 0, but again with that increment here, so that top bit's 1, but all the other nibbles are 0, and that's because we're starting at the very beginning of the memory range, which will effectively be the top left of the screen because of these settings here with the scrolling and things. So that's what we're doing here. And then we're setting up to fill the entire size of the screen here. We're using X, Y, and A here as a big loop counter. And we're writing A as a byte to the screen by storing it to D1 here. So before here, storing to D1, we're setting up configuration registers, but now it's physically saving bytes to the screen memory. And as soon as we save those bytes to the screen memory, they'll be visible, which is quite nice. So we're subtracting 1 each time so that our loops work nicely. But effectively, once we've done all of this, we've filled every byte that's visible on the screen with a colored pixel. And that's our test. So that if we just put a JMP star here and run again, we've got our nice pattern here, but we've got no text. And of course, if we just put it any higher up here, if we put it here, for example, well, what we've effectively got here is whatever was left in the memory from, you know, what was previously run, or the previous screen that was shown, which was probably a tile map or something. So anyway, you can see here that the point I was just making is that this is the code you would want to start stripping out probably if you were starting your own code and not using mine. What my code does beyond that though is it shows a hello world message here. So we're loading in the address of my text. You can see my text here. It's character 255 terminated, which is a common thing in all my tutorials. I know you probably prefer 0, but that's not the way I do things. And then we've got here our set0HML command, and I've also got another one we're going to see now, because the print string command is very basic. Effectively all it does is it just reads in bytes until it gets to 255 and repeats. There's a new line command. We're not going to go into those because, to be honest, they're the kind of things that I've covered in my other tutorials already, and really I'm assuming you know some 6502, because this would be a bit of a strange thing to take on if you've never done 6502 at all before. So I'm hoping you can figure those out yourself anyway. Now we're going to be looking at this print character routine, and what this does is it takes a value in the accumulator and it simulates printing a character to the screen, kind of like a firmware function might do, but we're going to write our own bitmap routines and calculate it from our bitmap font. So we're totally firmware independent here. Now for doing this, we're going to add a new command. We've got our set0HML command here, which used A, Y and X. We're going to have an add command here, and there's two versions here, one that uses A, Y and X and one that uses Y and X here. Basically the Y and X one just sets the accumulator to 0 before it runs. And so we're reading in the current L, M and H values from the registers there, from the hardware registers that is, and then we're just adding X, Y and A here, effectively increasing these. So as I say, it's pretty straightforward, but it's basically very handy because we can now set these registers A, Y and X, run this, and it will increment things. And we're going to use this to move down a line. Now each line of the screen is 320 pixels wide. Each pixel is a byte, so the screen is 320 bytes wide. If we want to move down a line, we just add 320. Pretty straightforward, and we'll see that in a moment. So here's our print character routine. So our print character routine will run, and the accumulator will contain the character we want to show. So a letter A, for example, something like that. Now the font I use in my tutorials doesn't have any characters below the space character, character 32. So character 32 is the first character in the font. And so because of that, we're subtracting 32 from the accumulator, and then we're storing it in a temporary register here, ZAS, which is a 0-page entry. Not really a register. I tend to call them registers because I think of them as Z80 registers. Anyway, once we've done that, we're now backing up a bunch of our other functions here. We're backing up X, Y, H and L because we're going to need those, but maybe our other code was using them. I'll show you some more advanced code that does need them, and that is why I'm effectively backing them up. Now we get our accumulator back. And what we want to do is we want to calculate offset within our font. So our font has 1 bit per pixel. So each line of our font, the font's 8 by 8 pixels. So each line of our font's a single byte. 8 lines tall the font is, so that's 8 bytes per character. So if we want to calculate the offset of the current character in the accumulator once we've subtracted 32, we multiply by 8. Now multiplying isn't a thing in the 8-bit world, so what we do is we do bit shifts to simulate that. So if we bit shift 1 once to the left, it will become 2. If we shift it again, it will become 4. If we shift it again, it will become 8. So we bit shift 3 times to the left, and that gives us the offset within the font of the character that we want. Now if you don't understand that, don't worry, just use the code as it is here. You could have done a loop and repeatedly done add commands, 16-bit add commands, but this is the faster way of doing it. So we do our shifts here to effectively multiply by 8. Then we add the base of the font. The font is in memory. I'll just show you it here. So we're loading in our font from this file called font96. Now this is because it's a 96 character font. This is also available in the sources download. So, go ahead and grab that. So once we've got to this point, effectively we've added the base, we've added the offset. So HL, these 0-page entries, now contain the source destination of the character that we want to show on the screen. So we've done the first part of it. Now what we need to do is we need to calculate the memory destination that we want to write to. Now I've got 2 memory bytes defined, cursor Y and cursor X. These start at 0 because that's the top left of the screen. And we need to calculate what that cursor position in characters is represented as a byte position in memory, because effectively we're doing all of the work of the firmware. So when we've printed one character, we need to remember that the next character needs to be printed one character to the right of that, so that we are printing readable text at the end of it. So, and that's what we're doing here. So effectively, we need to take our cursor Y position, multiply it by 320, because 320 bytes per line, times 8, because of 8 lines per character. So cursor Y is in characters, you see. Now, again, we don't want to do repeated additions of 320 for all the lines. So what we're going to do is effectively use bit shifts to multiply the cursor by this bit combination here. And a reason I've shown it like this is if you look at where I'm storing the cursor Y here, I'm storing it in ZE, and I'm using ZD as the top byte, so I'm effectively using them to simulate this pair here. So when I shift 1 to the left and then store, and then I shift another 2 to the left here, and then add the original one and store again, what I'm effectively doing is building up this bit combination here by repeated shifts and additions, and that's the fastest way of doing it, although I admit it gets a bit confusing, but it does work. So again, if you don't understand this, you could replace it with just a loop repeatedly adding 320 if you preferred, but this is, I believe, the better way of doing things, and it's the best way I can cope with doing things, shall we say. You know, with my limited mathematics, this is the current limit of my ability, shall we say. So there we go, that's calculated the Y position. Now what we need to do, it's a mistake there, that should be cursor X. What we need to do now is do the same for cursor X, because we've now calculated the Y line, but we need to offset for the X position as well. So cursor X times 8 is what we need to do here. Now that's much more simple. We just rotate 3 times to the left here, and we can see that happening just here. But then we need to add the value we've calculated here. We're using the accumulator and E here. So the accumulator is this byte here, and ZE is this byte here. I use the accumulator for 1 byte in each case because it's faster. This is a 2 byte command. This is only a 1 byte command. So by using the accumulator rather than a ZD or something else in the 0 page, I'm saving some bytes and some time. So I'm shifting these here, but then we need to add the result with any carries that have been built up to the other bytes. So we're transferring this to X, which is the bottom byte of our 3 when we call set0HML. Then we are getting the Y and adding with the carry this part that we've calculated here. And then what we're doing here is we are doing the same for the top byte, the D part. We're adding with carry because this might have produced some carry. And we're setting that top nibble to 1 again because we need to turn the auto inc on, because otherwise, you know, we're not going to be able to write many bytes. And then we run our set0HML, which will use A, Y, and X to set the top, middle, and low bytes of the memory address. And now we've got the position where D1 will write to the bytes to the screen, and our HL is the source address still of the source data. So what we want to do now is we want to convert a 1 bit per pixel font into an 8 bits per pixel screen. Well, how do we do that? Well, what I'm doing is I'm shifting 1 bit off the left hand of the source data, the font, and then I'm shifting that into a new byte and shifting that into the screen. So this is effectively setting all the colors to either 0 or 1. So we're going to need to do 8 pixels per line, and I'm using the X register here for that. So we load in a byte from HL, which was the data for the font. We're using Y as an offset because we're going to use that as a loop down here. And then we're storing the byte in ZAS, and then we're repeatedly popping off a bit of ZAS and rotating it into the accumulator and then storing it to the screen. And this is setting 1 pixel each time. So we're just repeatedly doing that, and each time we're just looping back up to here until X reaches 0. When X reaches 0, we've done 8 bytes, 8 pixels, time for the next line. So we need to move down a line. Well, each line of the screen is 320 pixels wide, but we need to move to the left-hand side to start drawing the next line again. And we've just written 8 pixels. So if we subtract 8 from 320, then we will get the amount we need to shift by. So we're setting Y and X here, and we're doing that calculation and just altering the memory address here, and that will move us down a single line. Now we restore our Y register here, and we increment it, and then we see if we've got to 8 yet. Now, if I'd have done a decrement here, then this comparison would have been easier, but that would have meant that the font would have appeared backwards. So that's why I've done it that way. We repeat for all 8 lines of the font here, and then Once we've done that, we have actually drawn the character. So what we need to do next is just check if we've reached the end of the screen, because if we have, then we need to simulate a new line. Otherwise, we'll start writing to weird memory and something strange will happen. So what we're doing here is we're increasing cursor X, seeing if we've got to the end of the line. If we have, we're calling this new line function. And you can see that's just setting X to 0 and increasing Y. Now, once we've done that, we're done. We just restore all our registers and we return. And that gives us this. So there we go. Now, there was a good reason that I was backing up these registers here. Not really a good reason in this example, but I've got my more advanced example here, and this is using the monitor function, which I've written and I use in all of my tutorials on all of my platforms. It's a simple monitor and amendment function that helps me out when I'm learning a new system and maybe the emulator doesn't have any monitor functions. So if we run this version here, you can see we've got some hello world messages again, but we've got a dump of the current status of all the registers here, and then we've got a dump of a bank of memory here. And that's the point I'm trying to make here. Once I've got print character working reliably on any machine, I can then use my monitor tools to debug things, and that really helps when you're starting out and you don't quite know what's in memory, or your software's malfunctioning and you don't know what values are being returned from hardware registers and things. So this really helps me out a lot, and as I say, that's one of the things I think is good about creating your own bitmap functions and doing everything yourself without the firmware, because you can make your own tools and really build things up. Anyway, that's all we've got for today. So we've had a look at how to do the simple bitmap screens on the X16. Personally, I found this really easy to work with. I've found it very pleasant, apart from that problem with the 4-bit per pixel screen. No problems at all, really. It all worked very logically. The examples were very good, especially since, as I say, this is my understanding is this is a really early stage of development, this hardware. So yeah, very interesting. And if you're into your 8-bit programming but you fancy a bit of 256 colours, then it's certainly an option for you. Anyway, if you like this and you want to see more, please let me know. Thanks for watching today. I hope you've enjoyed it, and goodbye. If you enjoyed today's lesson, please check out my website. We've got tutorials, source code and development tools for 6502, 68000 and Z80 systems, and a lot more systems coming in the future. We're going to be covering the 8086 and the ARM and a few other things as well going forwards. And if you've liked this lesson, if you've got questions, comments or suggestions on how it could be made better, please consider signing up to my forum. It's free, of course, and you can come along here and you can make suggestions, you can ask questions. And if you've got assembly projects you're working on, please let us know what they are. Maybe show off a few screenshots, tell us what things you've found interesting or what tricks you've come up with, because we'd love to know about it. Anyway, thanks for watching today, and goodbye.